Right, so now I'd also like to talk about some properties of probability distributions. First, I want to start with a quick reminder of what we learned about sample data earlier in the semester and what we saw when we were working with frequency distributions. When you have data displayed in a frequency distribution, if you find the mean of that data, and here we're talking about numerical data, if you find the mean, you call it x bar, and it's the average value in your data that's displayed in a frequency distribution. You can find a standard deviation for your data, which is referred to as S, and it tells you how spread out or clumped together your data is that you have displayed in your frequency distribution. And we refer to these as statistics. And in general, anytime we're talking about numbers we're calculating to describe a sample or something that's going on in a sample, we refer to it as a statistic. In a probability distribution, we have some similar concepts, but they have different names. In a probability distribution, you can also calculate a mean, but we refer to it as mu rather than x bar. This is one of those things that I think is very annoying to students in students in statistics classes, because you'd think, why are we giving new names to the same concepts? But as you'll see, we'll be distinguishing between probability distributions and populations and samples in more meaningful ways later on, so it will make sense to be giving them different names. But for now, the thing to keep in mind is that when you're looking at a mean in a probability distribution, it's going to be called mu. A probability distribution can also have a standard deviation. And the standard deviation here is going to be given by the Greek letter sigma. This is a lowercase sigma, so we've met an uppercase sigma, which looks like a big E. This is a lowercase sigma, which looks like a circle with a thingy on it. And we refer to these as parameters. And as a quick note, when we talk about probability distributions or population distributions, we'll be using the same terms for each of those because they're essentially the same thing. I'm not going to get too much deeper into that right now, but these terms will come up again when we're talking about population values. To illustrate this, I want to show you examples of means and standard deviations from distributions of these double coin flips that I've been talking about. So here's how we'd come up with the frequency distribution for a double coin flip. We would, I'm not going to go to the document camera for this, but flip our coin, call that one event, and then record the number of heads that we got. And so I just flipped my two coins. I got heads and then heads. So I'd record that as a frequency of 1 for 2 heads. And I could do this a couple more times. So I'm flipping my coins. I just flipped them again. Sorry, I'm throwing my camera all over the place. And I just got heads and then tails. So I'd record heads and then tails as 1 head. And I could keep doing this, and if I did this over and over again, I would eventually be able to fill out a frequency distribution like the one you see here, where I've recorded the frequency of the number of times I got each of these outcomes. So I just did it again. I got 2 heads, so I would record that as a frequency of I would record that as an outcome of 2 heads, which would go into that frequency column. Did it again. This is one of those things that works so much better when I'm in a classroom and I don't have multiple cameras and like multiple angles, so sorry for the wackiness here. So I just did it again. I got tails and then tails. Doing it again. Heads and then tails. So that's 1 head. Doing it again. Heads and then tails. That's 1 head again. I'm only going to do this a couple more times, then I'll show you why I'm doing it. Did it again, got heads and then heads, so that's 2 heads. Tails and then tails, so that's 0 heads. Heads and then tails, so that's 1 heads. And then heads and then heads, so that's 2 heads. So I'm going to stop now. So what I've been doing as I've been flipping these coins and sort of awkwardly talking you through it is writing out the numbers of zeros, ones, and twos that I got. So every time I flipped my 2 coins and got 0 heads, so in other words, 2 sets of tails, I put a check mark there. Every time I flipped my 2 coins and got 1 heads, I put a check mark. Every time I flipped my coins and they both came up heads, I put a check mark for 2 heads. And so in doing so, I'm essentially filling out a frequency distribution, where here I have these possible values that I can get, 0, 1, and 2, and then a frequency with which each one occurred. So specifically, of the 10 times that I just flipped these coins, I got 0 heads 2 of those times, I got 1 head 4 of those times, and I got 2 heads 4 of those times as well. So what's shown on the slide here as an example frequency distribution would be an example of a distribution that you could get doing the same thing. So with 10 flips of the 2 coins, you might have an example where you got 0 heads 1 time, so of the 10 flips, you only got tails and tails 1 time, where you got 1 head 6 times, so of the 10 coin flips, 6 of those times it came up with either heads and then tails, or tails and then heads. And then with, of those 10 double coin flips, then you also had 3 times where it came up heads and then heads for a value of 2 heads. So this is a frequency distribution based on 10 double flips of the coin, like what I just did, that you could kind of see. And the point of all this is that with this frequency distribution that you've created, you can calculate a mean and standard deviation. So in the example one I have up here, if you have 1 0, 6 1s, and 2 3s, you can add those all together and get a mean of 1.2. So the average number of heads that I got in this example frequency distribution here was 1.2. You can also calculate a standard deviation for those values. And if you do that, you get 0.63. So in counting up the numbers of zeros and ones and twos, we're looking at data in the same way that we've been looking at it throughout the semester. We have some number of different values that we can get, and we're looking at how many times each one appeared, and then we're calculating descriptive statistics that tell us, on average, how many heads did we get, and it also told us about how spread out our data are. On the other side of this slide, you can see a probability distribution. And this is the probability distribution that we calculated using the rules of probability. You can also calculate a mean and standard deviation for your probability distribution. And if you do this using formulas that we're not going to get into in this class because you don't need to, if you calculate these though using formulas, you get a mean of 1 and a standard deviation of 0.71. So again, that funky looking sort of U letter is called mu, and the other one is sigma, where mu is the mean of your probability distribution and sigma is the standard deviation of your probability distribution. What these tell you is that if you're to flip a coin 2 times, record the number of heads that you get after each double coin flip, you would expect the average number of heads you get to be 1. That's what that mu tells you. That tells you that the mean that you would expect, based on this probability distribution, if you were to flip coins and record the numbers of times you get 0, 1, and 2 heads, you would expect the average number of heads across all your coin flips to be 1. And you would expect the standard deviation for all of your coin flips to be 0.71. And so if you look at the example frequency distribution and the probability distribution, what you can see is that the sample mean, so x bar or 1.2, is pretty close to the mean for the probability distribution. And this is because the probability distribution is telling you that the most likely mean you're going to get for all of your coin flips is 1, and it comes out to 1.2 in our actual data. The probability distribution tells you that the most likely standard deviation you're going to get is 0.71, and you can see that we have a standard deviation of 0.63 in the example frequency distribution, which is pretty close. So what the probability distribution is doing is it's telling you more or less what you should expect your actual data to look like. So we know that this is the pattern of results you should get when flipping coins and counting up the number of heads. And then when you actually do it, you can see that you come up with a somewhat similar set of results. So to sum up the relationship between probability distributions and frequency distributions, a probability distribution tells you what to expect if you actually complete a bunch of different trials. So if you actually flip a whole bunch of coins, what pattern of results should you expect? If you were to actually pick a whole bunch of crayons out of a pot, what pattern of colors should you expect among the crayons that you picked out of the pot? And so, as an example here, sort of putting these two things together, if you're thinking about the number of heads you get in 2 coin flips, the probability distribution tells you the probability of getting each possible outcome. And it also tells you in your sample, so in all of the coin flips that you do and record the outcomes for, what percentage of each number of heads should you expect? And you'd expect in your real data to get 25% heads, 25% zeros, 50% ones, and 25% twos as your outcomes. But you may have noticed that in my example on the slide, and then also when I actually flipped 2 coins 10 times here, I didn't get exactly what I would expect. And if you do this quick math here, 2 zeros out of 10 means 20% zeros instead of 25%. 4 ones out of 10 flips means that 40% of my outcomes were ones. And 4 twos out of 10 flips means that 40% of my outcomes were twos. So it's a little bit different than my expectations here of 25% zeros, 50% ones, and 25% twos. The reason for this is that we're dealing with probability, and this means that random chance means that you may not get exactly what you would expect. And although the probability distribution tells you the most likely set of outcomes, it doesn't necessarily mean that you're going to get exactly that set of outcomes each time. So anytime you're doing double flips of coins, you should expect about 25% of those double flips to give you 0 heads. But due to random chance, so you just happen to flip a couple more, heads than tails in your set of coin flips, that sort of random chance means that your actual frequency distribution can end up looking different than your expected distribution based on the probabilities. And this is also why in the example that I showed on the last slide, the mean and standard deviation differed. So the probability distribution and its mean and standard deviation tell you the mean and standard deviation that you should expect in any data that you collect. But when you actually do it and you actually run through the trials and record your outcomes, random chance means that those things might differ as well. So you might just have a couple extra heads, like I did in this example, or you might get extra tails, and it could look different than what you'd expect. And that's because, again, we're working with probability, so we're not looking at anything that's certain, we're just getting a sense for what the most likely pattern of outcomes will be. But in what you actually get, it's often going to be give or take a few. All right, so the last thing I want to talk about today is the relationship between probability and probability distributions and samples. And I think I've already hinted at it a little bit on this set of slides, but I want to talk about it more formally now as well here. And specifically, the idea that I want to talk about is that samples are essentially made up of repeated trials based on some probability distribution, where the outcomes are recorded as variables. And so I want you to imagine drawing 10 crayons from a really, really big crayon pot and recording whether the crayon is red as your outcome. So not exactly the example we had before, but similar. You've got a really, really big pot. Imagine it's full of lots and lots and lots of crayons, and you're going to draw 10 crayons from that pot and record the outcome in terms of whether that crayon is red. If you're to draw 10 crayons, you could think of that as having 10 different trials, where each of those times your crayon's either going to be red or not red. Right, so you have a really big pot, you're going to draw a crayon 10 different times, and from those 10 draws, you're going to record the color of the crayon each time. And specifically, you're going to record whether it's red or just something other than red. If you do that, you have 10 different trials and 10 different outcomes, because you drew 10 crayons and each of them was some color. So for each one, you recorded whether it was red or not red. You could also think of this as a sample of 10 crayons that all have different colors. So you drew them 10 times, you recorded each one, and you end up with a sample of 10 crayons that are all different colors. And because you now have a sample of 10 crayons that have different colors, you can think of the color as a variable. So it's some characteristic that differs across those 10 crayons that you drew. So in this way, samples are based on probability. And each time you include a member in a sample, so each time you pull it out of some larger population and record some characteristic, you're essentially doing a trial, like in probability, and recording an outcome. And then you could go even further and calculate the number of red crayons out of the crayons that you drew, and that would be your sample statistic. So again, imagine you do 10 crayon draws from a really big pot, record the color of your crayons from each of those draws. That means you have 10 of these trials and 10 different outcomes. You can also think of that collection of outcomes as a sample of crayons where the variable is the crayon color. And you could calculate the percentage of crayons that are red or the number of crayons that are red, and that would be an example of a sample statistic. So that would be a description of the actual set of crayons that you have drawn from your big pot. Because of what we know about probability distributions, you would expect that the percentage of red crayons that you drew would be about the same as the percentage of red crayons that are in your pot overall, because that tells you the probability of getting that number of red crayons. Again, you expect your sample to resemble your population. But that's something that we'll also get into in a bit more depth later. But for now, just focus on the idea that if you repeat these probabilistic events, so if you draw M&Ms over and over again, if you flip coins over and over again and record your outcomes, it's similar to coming up with a sample in which you are drawing some sort of member from a population at random and recording some sort of outcome as a variable. Another example that sort of brings us more into the idea of samples that we talked about so far would be to imagine randomly calling 100 New Jersey residents and asking them whether they supported legalizing marijuana this past year. So here, instead of drawing crayons from a pot, we're essentially drawing people from a state population. But it's the same idea. And if you make 100 calls, it's like having 100 trials. So we're essentially drawing one person each time we make a call, and we are recording some outcome, which in this case would be their opinion about marijuana. If you do this 100 times, you end up with a sample of 100 people who all have different attitudes about marijuana, in the same way that you ended up with a sample of 10 crayons that all had different colors. This means that in this sample of 100 people who you selected and asked about their attitudes, you now have a variable, which would be their attitudes about marijuana. In the same way that if you pick crayons of a whole bunch of different colors, you have crayon color as a variable. And then if you wanted to, you could calculate the percentage of people in your sample who supported legalizing marijuana, and that would be a sample statistic. In the same way that you could calculate the percentage of red crayons in your sample, and that would be a sample statistic. So again, the takeaway from this is that samples are based on probability, because each time you select a member into a sample, it's like a trial, so an event that generates some kind of outcome, and then the outcome is whatever observation you have on whatever it is you're measuring. So whether you're drawing a person and asking them their opinion, or you're drawing a crayon and you're recording what color it is, you're populating your sample, so you're creating your sample by doing lots and lots of these different trials and then recording the outcomes each time. All right, so the final idea that I'm going to introduce today is one that will also keep coming up throughout the semester, and that's the importance of sample size, and in thinking about samples as probability. So if you think about a sample as being based on the outcomes of many, many repeated trials, large samples would involve a whole lot of repeated trials, while small samples would only involve a few trials. So if we're thinking about crayons, if you have a sample of 10,000 crayons, that means that you drew a crayon out of your big crayon pot 10,000 times. On the other hand, if you only have 10 crayons in your sample, it means that you had that trial, so that process of generating an outcome, drawing a crayon, only 10 times. This means that large samples are more likely to look like the population they came from, that is, to look like the probability distribution that they came from, whereas small samples are more likely to differ from their population and from their probability distribution just by chance. So let's go back to this idea of drawing 10 crayons and recording whether they're red. So whether the crayon is red is your variable, and you're going to end up with a sample of 10 crayons that differ in their color, and we're going to record, again, how many of those crayons are red. If you have just a few extra red crayons compared to what you'd expect based on the probability distribution, you'll end up with a noticeable change in the percentage of red crayons. So with the probability distribution that we had earlier, where 8% of our crayons are red, you'd expect about 8% of your crayons, or 1 out of 10 crayon is as close as we're going to get there, to be red. But let's say that you just happen to draw 4 red crayons out of 10. That's 3 extra red crayons that you just happened to draw when you were drawing crayons out of your big pot. Well, if you draw 4 red crayons out of 10, now you have 40% red crayons just by chance, because you happen to draw a few extra red crayons in some of your trials. And that leads to a really noticeable change in the percentage of red crayons. And it's something that we saw as well when I did the coin flips, where I did 10 coin flips here, and you end up with a distribution that's a bit different than what we expected. And this is because when you have relatively few trials, so you're looking at 10 crayon draws or 10 double coin flips, there's more opportunity for a few unlikely events or a few unlikely outcomes to change your frequency distribution. But let's imagine now that you have a really, really big pot of crayons and you're going to draw 10,000 crayons and record whether they're red. You still expect about 8% of your crayons to be red, which comes out to about 800 of those 10,000 crayons. Now imagine that you happen to draw 3 extra red crayons, the same way that we did in the first example. Well, 3 extra red crayons, when you're looking at 800 red crayons, is not a big difference. And so adding those 3 extra red crayons into your 800 out of 10,000 red crayons isn't going to change anything. 800 out of 10,000 or 803 out of 10,000, it's basically the same percentage. So when you have a lot of events, having a couple of unlikely events happen isn't likely to change what your overall pattern of outcomes looks like. And the main idea here is that if you repeat probabilistic trials over and over again, the unlikely events tend to cancel each other out. So you happen to draw a couple of extra red crayons. But then you keep drawing crayons, and then you're going to have some events where, you draw fewer red crayons than you'd expect, and then some where you draw more and some where you draw fewer. But it evens out over time as you repeat this 10,000 times. Whereas if you're only drawing 10 crayons, it's like, well, we got a few extra red crayons, but now we're done drawing crayons. So we're left with a much bigger percentage of red than we would expect. Whereas again, if you were to do it 10,000 more times, chances are those unlikely events would even out and you'd end up with about what you'd expect. You can also think about this in terms of samples in the more traditional sense. So let's imagine that you pick 10 people at random and ask them whether they support legalizing marijuana. If you have a couple of people out of those 10 with unusual opinions, you might end up with a really skewed sense for what people's attitudes about marijuana are. So either you have a few people who are much more gung-ho about legalization than you'd expect, or you have a few people who are much less excited about legalization than you'd expect. And based on those 10 people, you could end up with a really, really different picture of what's going on with just a couple of people having different opinions. But now imagine that you're sampling 10,000 people and asking whether they support marijuana legalization. If you have a few people with unusual opinions, similar to the crayon example, it's not going to create that much of a different picture. So if you have 3 people who have unusual opinions out of 10,000, that's negligible, whereas 3 people out of 10 would make a huge difference. And the same idea also applies that unusual outcomes tend to cancel each other out. So of your 10,000 people, you might have a few people who are sampled who have really extreme views on one side. You might have some people who are sampled who have really extreme views on the other side. But it's unlikely that you're going to only end up with one set of extreme views, because the more people you talk to, the more those extreme views are going to sort of even each other out, and you'll end up with something that's more representative of the population as a whole. And so again, these are ideas that we're going to come back to later in the semester, but I like to get you guys started thinking about this when you're thinking about samples in terms of trials, because it's good to think about how, as you take samples, you have outcomes that are just based in probability, and so unlikely things are unlikely, likely things are unlikely, or are likely, and that contributes to the makeup of a sample. And again, with this slide, the point is that when you have only a few trials, you have more chances for unlikely outcomes to happen and then really dominate what you're looking at. Whereas if you repeat them over and over and over again, chances are any unlikely outcomes are going to even out over the long run. All right, so I'm going to leave you guys with that today. I know that talking about samples as events and trials is often a little bit hard to absorb at first, so I say, just focus on the main ideas here, which is that you can think of samples as being based in repeated, outcomes from probabilities, and the more of those you have, the more likely they are to look like the probability distribution or the population that they came from. So with that, a couple of reminders for the week. Problem set 5 is going to be due this Sunday, as usual, at 11:59 p.m. There's the usual optional review session from 2:30 to 3:30 on Wednesday, or if you want to talk to me at a different time, just email me. I will say so far nobody has showed up since the first week, so hopefully that means you guys are feeling comfortable with the material, but if ever you do want to talk to me in person about what you're doing or get any more examples, just remember that I will be there from 2:30 to 3:30 on Wednesday, or by appointment if Wednesday doesn't work for you. Or feel free to leave a comment on Canvas or just email me with questions, and I will generally get back to you pretty fast. So with that, I'm going to sign off and have a great week.